Hello, welcome. We are going to verify the following statement, which is written as: we know that the fluid passing through a conversed nozzle will have the sonic velocity at its throat or neck. It means the diagram shows a conversed nozzle here. The velocity, if passing through this nozzle, will have the sonic velocity at the throat. Second one is governing condition for the above statement is the value of pressure ratio between the critical pressure, that is the pressure at the throat, and the inlet pressure of the nozzle will always vary from 0.53 to 0.57. It means the critical pressure here, when the fluid attain its sonic velocity, and the pressure that, that is called the critical pressure at the throat, and the ratio of the pressure at inlet will have approximately 0.53 to 0.57 for ideal cases. This is the condition for sonic velocity at throat. It also we will visualize velocity profile of the fluid flowing inside any object having the circular cross sections. Now let us join to the Ansys. This is the Ansys window. I will go for fluid fluent. Yeah, just open. Now you can change the name here. For example, I am going to put name converse was nozzle. Now double click on geometry. The design modeler is starting working here. It is shown at the bottom. Okay, it is open. Now select XY plane. Click on face. Change the unit from meter to millimeter. And click on sketch. Here, the sketch, you can see line, tangent line, many tools, geometrical to construct a geometry. We have these different tools here, options. For example, if I do this, we can get so many tools, so many geometrical tools. Line, tangent, polyline, polygon, rectangle, etc. So here we can choose polyline or single line, whatever is for your interest. I am going to choose line. This is the converse nozzle diagram, as we have seen here. 20 mm is the larger dia, and 12 mm is the smaller dia, and 25 mm is overall length. So we will see that the center line and the other half part of this nozzle geometry need to be symmetric. So click on constraint, click on symmetry, select center line, centers to point. Similarly, in this line too. Now we'll go for dimension. Select length and distance. Select 2 point. And drag anywhere. detailed view, we can see the L1 as it is being highlighted here, L3 highlighted here, and L4 is this. Now we can change the dimension according to our requirement. This L4 is 12 mm, 12, 20 and 25. 12. Change this 12. L3 is this 25. L2 is 20. Okay, this is the actual shape of nozzle which we need. Now click on concept, surface from sketch, click on XY, click on sketch 1. We are selecting sketch and apply and generate. Now we have got a surface, 2D surface, and this geometry you can import even some of the CAD softwares, Pro-E, Clio or CATIA. Now go to again sketch. We have to define some thought here, because this is a one surface and we will have to split into two parts. The surface need to be split in two parts. Now we have to have one line to separate this one geometry. So draw a line from here. This line also need to be constrained parallel to this line. Go to the constraint. Parallel, select parallel. This line and this line. Here it is already parallel. Now go for dimension. Distance between these two lines should be 3 mm. Change it 3 mm. More. Now click on tools, face split, select the surface, apply, click on tool geometry, select the line, apply, and then now if you see, the surface are divided into two parts, split it into two parts. Geometry is okay. Now next step is to go for meshing. Here we can see the geometry is tick mark. Now go for the meshing. Right click, edit, meshing shown here. Yeah. The geometry has been displayed. Now you can click on Z-axis. This is the geometry. Here we have separate tools, vertical lines, separate tools for lines, well, and also we have the body here. So we can control the meshing here. Right click on the meshing for method, automatic method. Change this all quad. Select all vertical tools now. Control plus for sizing. Number of division here we are putting 30. Again go for another line which is wall line, which is need the tool. These tools, this tool will represent the wall of nozzle. Control plus select all the lines. Click insert sizing. Sizing element sizing. Number of units 20. Okay. Now method edge we have everything we have. Fine now. Now go for this. Change the MS being generated. Yes, okay. Now we'll have some fine to define it. Some map face. Okay. Select this both the surfaces, apply and regenerate that mesh. Yeah, that's okay. Now next step is here the mesh is not ticked yet. Right click over here and update it. One thing we have to do again, we didn't define the inlet and outlet here. We have to define this is the inlet, this is the outlet. Okay, select this vertical tool, create name section, inlet. Okay. This is outlet. Yes. These lines will represent what? Okay. It's already missed. Rotate. Yeah, it is taken and updated. Now next step is go for setup. Double click. Starting fluent. Double precision serial is okay. Click on OK. Yeah, it's okay. Now general model, everything is okay. Here we need density list. Then go for model. Double click on energy of energy equations. Okay. Material until select air. Create. Here as ideal gas. Velocity, everything is okay. The constant for this specific heat is okay. Thermal conductivity is okay. Viscosity, we are calculating. This operator is calculating Sutherland. So select Sutherland. It's okay. Notice that. Close. Go for boundary conditions. Let pressure. Yes. The pressure here at inlet, in case I'm considering 2 bar. is 2. It's 5. Okay. Then outlet. Outlet pressure is assuming 0, minimum. Minimum means 0. Okay. The boundary condition will be defined. Solution method is okay. Solution control is also okay by default. Meters. Okay, here we have to create drag CD1. Okay, print and plot both, and wall zones, slab wall zones. Okay, propose solution initialization, select standard, compute from inlet. Now you can see the velocity at inlet in the y directions, and the temperature is ambient. Initialize. Okay. Now go for run calculations. Number of iteration minimum we need for this type of fluid print 500 to 1000. I'm keeping 500. Calculate. Okay. It is calculated. The iteration will continue till this line becomes a straight line, a constant line. Now it is varying since the iteration is on and it is continuing. Now you can see here the line is becoming straight. Even the iteration is approximately just 300 around. After 500 it will become straight and constant. The solution will get the exact result. Calculation is completed. The line is straight and the iteration is completed 500. Okay. Now go for this graphic and animations. Select contour. Here, select display. This is the lines from here. Here. Now you can see here that the inlet zone, the pressure is 1.8 Pascal, approximately 2 bar, 1.8 bar. This whole red is indicating 1.8 into 10 to the power 5 Pascal. It means 1.8 bar. Whereas the outlet around the throat region The pressure is indicating somewhere this green zone, because we have split it in two parts. One is the throat part and this is the outlet part. It's showing somewhere it is approximately 9.61 green part, 9.61 into 10 to the power 4, it means 0.96 bar, 0.96 bar. Now the ratio of this pressure and this pressure, it means if we divide 1.04 around this pressure with this pressure 1.8, will come approximately 0.537. That will be the critical pressure. So the result we will show in we'll see in graph also. Now we'll see the velocity profile. The velocity. What will be the velocity? Here the velocity should be approximately 1 Mach. Select velocity. Select Mach number. Display. Yeah, here you can see the red zone and yellowish zone. This red yellowish zone is approximately showing red zone outlet pressure. Velocity at the exit is approximately 1.02, say 1 Mach. That is the result. Now we will see this the same in graph. In close the window. You can go for plot. So I plot. Plot. Here the pressure we can see this is the inlet pressure approximately 1.8, somewhere 1.8 bar, and the outlet pressure is somewhere here 0.6. Thereafter the pressure is constant. Here. If we divide this pressure to this pressure, the value should come 0.53 to 0.57. That is the critical pressure, and that is also the condition for sonic velocity at throat. Now we'll see the velocity. Here the velocity is at the outlet is 1 Mach. This is 1 Mach. This is also our theory is proved. Now you can have a photograph of this. See, Here you can change the name, graph, graph 1. Okay, see the preview here. This is the one map here about it. And thereafter the velocity remain constants. The theory is proved. It is verified. You can see here in the graph. Close the tab. So close this tab and close these all tabs. Now we will see the velocity profile. Click on the result. The starting CP post here. This is more user friendly. The geometry has been imported here. Now go for volume rendering. It's okay. Select inlet, walls, and outlet. And here, click on the z-axis. Here you can see the pressure velocity. Okay. Yeah, here is the same thing. Now we want to see the profile of the velocity here in a circular cross section. Go for contour, streamline, sorry, not contour. It's okay. And starting from inlet, apply, and see the simulations. This reduce the speed. Let us go a little bit slow. And this way. Now the fluid is moving in this shape. In the cross section, having a circular, the velocity profile in this shape. Now all the three things we have been verified and the result found satisfactory. Thank you for watching this video. Close. Close. Thank you.